Okay, so for today, Professor Olivier De Weck, I don't think he needs much introduction. He is from MIT. He's a professor there in engineering systems division, and he holds numerous degrees from ETH, very distinguished institute in Switzerland, and also from MIT, and he has long experience in industry as well as in academia. He's a program manager in aerospace industry in McDonnell Douglas, when it was still known as McDonnell Douglas. And he's worked in systems in different areas in systems engineering. One thing his bio doesn't mention is that he's also the co-director of the Center for Complex Engineering Systems in Saudi Arabia. I forget the name of the university. So he's world renowned for his expertise in systems engineering. Today he's going to talk about complexity in systems engineering. When it's complex, too complex. And then the first law of systems engineering, which always intrigues me when we talk of laws of systems engineering, talk of laws of thermodynamics and laws of motion, but is there such a thing as laws of systems engineering? So that will be a really interesting talk. So I'm really looking forward to it. Professor De Weck.
Thank you, Professor Jahangir. Ebad, thank you so much. Thanks for having me. It's great to have you here. Beautiful New England morning. Beautiful campus. I'm really impressed by UConn. This is my second visit here on the campus, so I think you're very fortunate to be here. As was said in the introductions, I'm at MIT. There's a few programs I'm associated with. One is the SDM. Maybe I'm just going to use my pointer here. System Design and Management Program, the Air Astra Department, and then IDSS, we had a quick exchange about it. It's a brand new unit at MIT called Institute for Data, Systems and Society, really looking at big systems, complex systems that generate a lot of data. So it's exciting. The other thing I want to mention is what I'm going to talk about today is joint work with Dr. Kaushik Sinha, who's a research scientist in my group, and then Narek Shugarian, who's a PhD student. And if I keep my fingers crossed, he should finish pretty soon. But you never know, right? It's research.
So, in December, I'm just curious.
Yes, that's the goal, December. So, three things I want to talk to you about today is why should we care about complexity? How do we quantify complexity? And then, eventually, how do we better manage it? And I'm going to start with a news item that will hit pretty close to home for most of you are aware that Pratt Whitney, which is one of the UTC companies, is pushing the envelope in aviation, particularly in the area of turbofan engines, geared turbofan engines. So one of the new, and this is a platform for a series of new engines. Cross-section is shown here. And so we did actually have a sponsored research project with Pratt & Whitney on the question of how much more complexity does this engine really have compared to a classic two-spool direct drive engine, and where is that complexity? And so the big deal here is this gearbox that you see here. It decouples essentially the fan from the low-pressure spool and allows roughly, it's a fixed gear ratio, but it allows the spool to go much faster and have higher thermodynamic efficiency, and then the fan to rotate somewhat slower, which gives you less noise emissions. So you get better fuel economy, less noise, but at the expense of more complexity. And we'll get into that more specifically. The issue now is putting this engine into production, delivering it. One of the key customers is Airbus. This is one of the options on the A320neo, new engine option. And you can see this is from a couple weeks ago, September 16th. The issues now is ramping up and really handling this complexity. So it says in the article, and this is all public, and we can debate how accurate these numbers are, but that over the years, Pratt & Whitney has invested about $10 billion in the development of this engine. That's a major investment. And that the engine itself has about 800 parts. Also, of course, a complex control system known as a FADEC. And this complexity is causing big issues. And so I want to use this example as one of the motivations why complexity quantification and management is really a critical issue. Yeah?
Just a question. So the premise is that this engine is more complex. I could argue that it's less complex because of the gear turbofan, because it's decoupling.
Right.
The low spool from the fan.
So it depends there.
And the number of parts is also lower in this than the previous generation.
That's right. So the complexity can be quantified, as we'll discuss, in the functional domain, in the structural or form domain, and also in the organizational domain. And you really have to look at all domains, and you have to look at not just part count, but the complexity of each part, the number of interfaces and types of interfaces. And then my big message to you today is you have to look at topological complexity. And even if the part count is lower, this engine has a high topological complexity. And a lot of that comes in not from the gearbox itself, but from all the supporting systems. The cooling, the lubrication, and then the engine control software is significantly more complex. So that's sort of a wake-up call.
Most problems are with the interfaces, right?
Yeah, so we'll get into that. But I want to start, step back in time a little bit and just ask you, I always try to read something that's not, this is sort of related to work, to research, but what have you guys been reading lately? Like a book that inspired you or that you would recommend to a friend or family member?
I've been reading this kind of Polish folklore, medieval folklore tale.
Oh, interesting.
Yeah, which is quite fantastic.
Nice. Anybody else? No?
Well, it's not fiction, but
That's fine.
but I'm an engineer and a guitarist, and I'm going to start building guitars, and so I've been reading guitar building manuals. But that's not quite as inspirational. It's more.
But it is your passion. It's great. So I read a book last year, which I highly recommend to all of you. And that's the book on the Wright brothers by David McCullough. And McCullough is a very well-known historian. He won the Pulitzer Prize twice. And he does a fantastic job tracing the history of, how the Wright brothers went from they tried many different businesses and failed and tried again. And of course, they were bicycle makers, right? They had a bicycle shop in Dayton, Ohio. And how did they create the first airplane heavier than air that was able to be to carry out powered flight? So I highly recommend this book. And so when you read the book, you realize that these guys didn't just sort of do the seat of the pants. They had a wind tunnel. They spent months and months and months observing birds, bird watching. How do birds fly? And one thing you see in birds is they don't have ailerons, right? Or flaps. They basically twist their wings. And so that was a big inspiration for the Wright Flyer. So if you look at the Wright Flyer as the first flying machine heavier than air, you can think of the complexity of it. What were the key parts? How did they interface? What were the functions of each of the parts of the airplane? And I would claim that we can quantify the complexity of the Wright Flyer and then compare that to the complexity of today's airplanes. So, for example, they used, you see here in this graphic, there's different parts that are highlighted. So they had a wheel hub here. This is for the landing. They had an elevator in front. One of the most interesting things is, I think, the control mechanism. So the pilot was basically in a lying down position and was lying in a hip cradle. So this is like a cradle, and then with the hip movement, the hip cradle would be attached to these cables, which were then attached to the wingtips. And so by moving the hip left and right, the cables would essentially actuate and work the wings. And that's essentially how you provided roll control, right? Pitch control through the elevator, and then there was a rudder. So that's pitch control and and yaw control, pretty traditional. I mean, we would recognize that today, but the wing warping was quite innovative and was definitely bio-inspired. The other thing is, of course, they put a lot of work into the development of the engine itself, making sure they have a lightweight engine that has a power-to-weight ratio much better than the engines that existed at the time. The development of the propellers was also a big challenge. And the engine was water-cooled. And there were even a couple instruments. One was essentially a pressure, dynamic pressure sensor that allowed them to estimate the airspeed. And the second instrument was a clock, so they could measure the time of flight. So they already had instruments back then. So since I mentioned, the evolution of complexity over time, I'm sure most of you have heard of Augustine's laws. Norm Augustine was the former chairman of Lockheed Martin, very thoughtful person, and he wrote this book called Augustine's Laws. Most of the laws are very silly extrapolations from the current state to the future, linear extrapolations, which are always dangerous. So this is the 16th law, where he claims that the cost of an individual aircraft has been on this slope here, which is steeper than the increase of the defense budget and the growth of the gross national product. And then here's the Wright Flyer, right? This is 1903. We just looked at Model A. And what's remarkable is that since first publishing this in the 80s, this is the 6th edition. He's been adding like the Joint Strike Fighter, right? The F-30, the JSF. We're still on that trajectory. So, we're still tracking with the 16th law. And the silliness comes in here. By 2060 or 2050, one single airplane will be so expensive and complex, it takes up the whole defense budget. And then, the Navy gets it on Monday and Tuesday, and the Air Force on Wednesday and Thursday. And then...
But do we really need them, though?
Do we really need them? That's the other... That's of course, the big question now. But
we can't pay the pilot either.
So why don't we just go to automation?
That's right. But the point is, we've been adding more and more complexity over time. And are we pushing it too far? So DARPA, as the Defense Research Projects Agency, has been very worried about this escalation in cost, not just in aircraft, but in all systems, and commissioned a study to try to quantify this slope here. You can translate the slope into an annual increase in cost. What's driving that? What's driving this escalation in cost? And so this was a 2008 study that came out and basically concluded that the annual escalation rate of cost for military aircraft in particular was about 10%, right? And the long-term average inflation rate in the US is about 3%, which is what you see here. So all the blue stuff on this is essentially inflation. Material, equipment, labor. So you can explain this 3% just by inflation. The biggest portion here is due to complexity increase. More functions, more robustness. The Joint Strike Fighter has the 3 major versions, the vertical takeoff and landing, the Air Force version, the Navy version. So you start piling more and more requirements onto the same system. And you see this large increase in complexity and cost. And so I talked about requirements explosion. This is one of my favorite charts. This is actually a chart that was first made in 1991 when the AIAA Multidisciplinary Optimization Committee was created. And it shows over time the functional requirements explosion in aviation. So let's go back to the Wright brothers. What was the requirements that the Wright brothers were working to? What was their goal?
Keep it like us.
Heavier than air flight.
Heavier than air flight, sustained flight, whatever that meant. 20 seconds, 30 seconds, in a straight line down the beach. That's their requirement. And that's shown down here. 1G flight. That's it. So, again, coming back to the book, what was fascinating is, so they had 1903, and for several years, because they did this on the beach, there were not a lot of spectators there. People didn't believe it. The population in the United States ignored this achievement. The media, the military ignored it. The Wright brothers went to the War Department and said, you know, this could be a big deal, and they basically ignored it. Part of the reason was because there was a competitor called Samuel Langley who had the backing of the establishment, but Langley was behind, even though he had a lot more resources. So in order for this to really penetrate into public consciousness, they went to France. They were invited by the French. They transported their airplane in crates across the Atlantic, rebuilt it essentially, and then conducted flight demonstrations for large crowds at a racetrack outside of Paris for months. So like 10,000 people would show up. And unfortunately, the airplane could only fly under pretty narrow conditions, right? Like too much wind, you couldn't fly it. And then flying around the racetrack, figure eights, different maneuvers, you started to have maneuverability became an issue. And being able to fly over a larger range of wind conditions. So by 1908, they were really, really famous. And people really acknowledged them as being the first in France. And then it kind of came back to the US. But you can see that the next set of requirements here was being able to maneuver and handle gusts, wind gusts. And then after that, corrosion control. We start making airplanes out of metals instead of fabric and wood.
That is when Sperry autopilot thing, 1912.
What do you mean?
The autopilot that was Sperry's.
Oh, I see. Yeah, so that's not shown here. So the ability to have autopilot, maybe we should add that here. But, this is sort of the basic increase in range, capability, pressurization as you go higher up, above 15,000 feet. You need to pressurize the cabin. You need to provide oxygen. And then you see a big spike in requirements during World War II. Radar transparency, the radar signature became an issue. And then we have another big increase in requirements during the Cold War. Things like not NEMP, being able to withstand a nuclear pulse, computerized information management, fly-by-wire is shown here. But you would put it earlier. But, those are all, and the more recent requirements are around product producibility, affordability, supportability. So it's pretty well understood that the reason that the complexity and the cost of these airplanes has increased is because we demand so much more of them. Wider range of operating conditions, more functions, and so forth. So we're going to start this discussion on complexity with two dimensions. The first one is functional complexity. Okay, so we require more of these airplanes. So the customers and then the competitors, this is, by the way, also fascinating in the Wright book, is even though they were the first, within less than a decade, there were dozens and dozens of airplane manufacturing companies out there. And one of the reasons the Wright brothers weren't as successful later is because they got involved in IP issues and so forth, and it became a very competitive industry, early aviation. And so competition, whether it's in the Cold War, it's military-driven competition or commercial competition, is at the root of these complexity increases. So the customers and competitors drive requirements which increase functional complexity. And then in order to handle that functional complexity, we need to implement more features, more technology, so that drives the system architecture, the design engineering that enables these functions. And then we see that reflected in what we call structural complexity. So structural complexity is what you can actually see and touch, including the software. It's the implementation of the system. This is what you can see. Functional complexity is what the system does, the function of the performance of the system. And then as you increase structural complexity, sometimes you get emergence. In other words, the system shows behaviors that you don't really want. Like flutter would be a good example in aviation. It's a high-speed phenomenon. Then you need to counteract that, that emergence, which adds new functional complexity, and you kind of go back and forth. So we'll start there, and then we'll complete that picture at the end. So I told you, I think we can quantify the complexity of the Wright Flyer, and we're going to focus mainly here on structural complexity in this talk. So this is shown here. This is what I call a design structure matrix, or some people call it an n-squared diagram. Essentially what it shows is the major parts of the airplane. Those are the rows and columns. It's an n by n matrix. And then on the off-diagonal cells, these different cells here show you the interfaces between the parts. And this is a big debate always in design theory. What kinds of interfaces are there? There are only four fundamental types of interfaces, even though you see lists of 15, 20, 30 different types of interfaces. When you really come down to it, there's only four. You can classify them into these four fundamental types. Physical connections, they're shown in black. So two parts are physically connected, which means that you can transfer loads across that interface, forces or torques. Red is mass flows, so there's some substance flowing from one part to another. It could be solid, liquid, or gas. Energy flow is in green, and then information flow is in blue. And we have all four types of interfaces here, even already in the Wright Flyer. So, for example, I mentioned the pilot, which is shown here. The pilot transmits information to, or gets information from the instruments. So from the instruments to the pilot. The elevator control, the pilot controls the elevator control and gets feedback from it. And the same is true for the hip cradle. Right? So the position of the sensor, there's a feedback loop between the pilot and the hip cradle in all three control mechanisms for your yaw, pitch, and roll. We also have mass flows involving the engine, and those are particularly the gas tank and then the water reservoir. So you had a gas tank, combust the fuel, and then the water reservoir to cool the engine. So in some sense, we already have the beginnings of everything we see in a complex airplane. If you start quantifying it at this level of abstraction, we have 62 physical connections, 4 mass flows, 11 energy flows, 9 information flows, and that results in a density of this DSM of about 7%, meaning that 7% of the cells in this DSM are populated. There's an interface there. The other thing that's interesting, we're going to come back to, is the average number of connections of a part to other parts is 5. In graph theory, we call that the mean nodal degree. How many connections does each node have? If you think of a component as a node, and it's 5. We'll come back to that later.
So how do you get the z squared? Should it be squared? Is it 1225 or 1225? The number of elements.
Oh, so you have to choose, when you do a DSM model of a system, you have to choose the level of abstraction.
Right, okay. What is the biggest DSM you've ever seen?
The biggest one I've seen is over 1,000 by 1,000, but it's actually pointless because you can't see anything.
Right.
So the experience with DSMs is that we get the most out of them when they're somewhere between 25 and 81. And basically what it is, it's a 2-level decomposition. If you go bigger, you have to go hierarchical, or you really don't get insights.
So do you think this was designed well, this DSM?
Well, the DSM is not designed. The DSM is basically a reverse engineering of the actual airplane.
Yeah, right.
So
they have done differently?
Well, DSMs, there are many different architectures of airplanes.
Right.
But, for their time, they were the first to succeed. So, in that sense, yes, they did well. But it was very iterative. It didn't. The version of the airplane that flew was not the first version. Like, this was a very iterative process. So hopefully I've convinced you that we should care about complexity. Now, how do we quantify complexity? There's a lot of literature on this. And we've certainly looked at a lot of the literature and worked on this for a number of years. And came across the work of Elaine Weicker. which we think is quite important and impressive. So Elaine Weicker is a software engineer, and she's an IEEE fellow. She was very, very highly recognized for her work. And this is going back to 1988. She wrote a paper called Evaluating Software Complexity Measures. And there's been a lot of complexity, proposals for how to quantify complexity of software. And what was remarkable about her paper and her work is that she doesn't propose yet another measure of complexity. What she says is, any measure of complexity that you propose needs to satisfy these criteria. And so they're known as Weicker's criteria now. So any valid metric of complexity should demonstrate the following characteristics. There's 7 of them. I'm not going to go through all of them. Just to give you a couple examples, it should be invariant to relabeling, and that's called isomorphism. So if you just relabel and reorder things, it shouldn't change the complexity. Changes in internal, this is a very important one, number 5. Changes in the internal architectural pattern without changes in system size impact the level of structural complexity. What it means is, let's say you have the same number of lines of code or function points in software, two different software programs. They look like it's the same size code, but one code has a lot of loops in it, a lot of nesting within. That's a more complex structure than code that doesn't, even though the raw size of the code is the same. That's what criteria 5 says. So essentially, we think Weicker's criteria are very important, and what I'm going to show you, we think satisfies Weicker's criteria for general systems, not just software. Okay, so here's the structural complexity metric that we've developed and that we've, I think, pretty successfully applied in recent years. And I'll show you where this comes from. So it looks a little scary, but it's actually quite simple. So the complexity of the system, we're going to calculate a single number, a measure of complexity, C, is equal to C1 plus C2 times C3. So there's 3 major terms. The first term, C1, is the complexity that resides in each individual component. So if you take the system, say the Wright Flyer, or an automobile, or whatever system, and you disassemble it completely, and you spread all the parts on the parking lot, each part individually has complexity. And different parts can have different levels of complexity. Some bolts, is different from a complex gear, right? So the alphas reflect the individual component complexities. Plus then, the complexity that's in the interfaces between the parts, those are the betas. So here we have a double sum because we're summing over that whole DSM, right? You're summing across the rows and columns, multiplied by this term here, and this is the really interesting one. So gamma is a normalization factor, n is the number of components in the system, and then E of alpha is called graph energy. So purely as a mathematical concept, if you have a matrix, you can calculate the energy of that matrix. It's called the graph energy. And the way you calculate that is by taking the singular value decomposition, which is probably the most important operation in linear algebra. You take the SVD, singular value decomposition of the matrix, and you add up all the singular values. So it gives you a measure of complexity just based on the structure of that matrix, and it's multiplicative. Okay, so that's how you calculate structural complexity. Where does this come from? What we did here is take a concept that already exists in quantum chemistry and generalize it to cyber-physical systems. So it's essentially the Hamiltonian of the system. So if you remember back to your mechanics classes, the Hamiltonian is a measure of the total energy of the system, including kinetic and potential energy. And in chemistry, people have asked, how do we quantify the complexity of a molecule, a complex hydrocarbon molecule? Some are very simple, some are very complex. So how do we do that rigorously? And essentially, there's this, it's called also configuration energy. So you see on the upper left, that's a hydrocarbon molecule. You have 2 benzene rings. carbon atoms, hydrogen atoms attached, and you can look at the abstracted version of that molecular structure. You calculate its graph energy, and then you know that a carbon atom is more complex than a hydrogen atom, and you account for that in the total complexity quantification. So the functional form of this molecular, of the Hamiltonian, is this alpha times the identity matrix for each atom, plus the second term here, which is a function of graph energy. And that's exactly the same functional form that we're using to quantify the complexity of more general systems, not just molecules.
But you also have one extra term right now.
Say again?
You also have one interface term.
That's right. So this beta term here. Yeah.
Okay.
That's right. So, how do you apply this to a cyber-physical system, not a molecule? Well, you need to understand the structure of that system. So here's a very simple, this is from Denman James's thesis. Denman is the lead for mechanical systems at Pratt. And so here we have a pump, motor, valve, filter, and a controller linked through these 4 kinds of interactions. So we can come up with the A matrix, which is our DSM. We calculate the singular value. And then the biggest challenge still today is determining the correct values for the alphas and the betas. Alphas are the component complexities, betas are the interface complexities. When you're doing it at the molecular level, we know what the energy is of an atom. We know the atomic number of the atom. So we have to, since we're not really operating at the atomic level per se, we have to define what is sort of our base energy level or base complexity level based on essentially the simplest component in the system. So there is some fuzziness potentially or some uncertainty around the alphas and betas. And to acknowledge this, you can calculate a distribution of structural complexity and then say, this is the mean, this is the mode. And you'll see that it's right skewed because you're multiplying C2 and C3. So we actually conducted, and this is part of Kaushik's research, a validation using human experiments. And the question really was, why does complexity matter? What impact does increasing level of complexity have on humans, on human cognition in dealing with these systems? And we said, basically, since the definition that we're using for complexity goes back to quantum chemistry, let's go back to chemistry and do an experiment to see whether it matters. So what we did is essentially recruit volunteers, and we gave them the chemistry sets that many of you have used in high school, right? The ball and stick models, and started them with simple molecules to essentially build these based on a set of simple instructions and pictures, and then step up the complexity. And what we measured was how long does it take them to build and correctly build these molecules. And if they make a mistake, they have to rework it, and that's included in the build time. And the hypothesis we had is that higher structural complexity leads to A, slower progress, because it takes you longer to understand what you're doing, what you're building, and B, a higher error rate, which causes you to backtrack and fix your mistakes, and that's included in the time. So without getting into too much detail, so we had 12 molecules, and their structural complexity ranged from 0.68 to 16, so not quite 2 orders of magnitude. And then we conducted experiments with 17 test subjects, and you can see essentially on this graph the mean build time versus the structural complexity. And the big takeaway here is that it's a nonlinear effect. So as the molecules get more complex, the build time increases superlinearly. It takes you more and more time as a function of increasing complexity. And if you model this as a power law, the exponent here is about 1.5, 1.48 based on these experiments. So what this means is the effort to deal with this complexity goes up less than quadratically, but more than linearly, about 1.5. Okay? And this is for cognitive reasons. Another interesting result in the experiments was, and this is an empirical observation, is to look how different people deal with the higher complexity molecules. And so we see this sort of scalloped curve. Some people they assemble a complex molecule exactly the same way they deal with a small molecule. And the problem is, you hit the wall here. There's a complexity wall. You just get overwhelmed. Other people, we observe them and they step back and they say, aha, there's benzene rings here. There's modules here in this molecule. And they actually build subassemblies first. And then they build the whole thing. But not everybody does this. So though people that can step up to a higher level of abstraction and see the modules, they basically manage to be on the red curve instead of the, and that's one of the reasons for the spread in build times that we observed. The spread goes up with more complexity. So to summarize on this, this is other measures of complexity that have been proposed, very simple ones like number of components, number of interactions or interfaces, number of loops, nesting depth. We believe that this matrix or graph energy-based measure is the most rigorous, and it's fairly easy to compute, and it satisfies all of Weiker's criteria. So that's why we think it's maybe not the only one, but it's a rigorous measure to use. Yeah.
A quick question. So Herbert Simon has this paper in the 60s, The Architecture of Complexity, in which he argues that his complex systems emerge in hierarchical fashion. Is hierarchy or modularity part of your metric in any way? Or can it be included? Because
it's naturally included. Because if the structure of the system is hierarchical or modular, and I'm going to get there now, that will be reflected in the graph energy.
The DSM will have that.
The DSM will have it, and you'll see it, and the key term is the C3 term. And I'll show you that there's a regime of C3 where those hierarchical systems exist. And we'll get there now, actually. So the last part of the presentation is, so what? Okay, so we can quantify complexity. Does it make any difference? How can we use this to better manage it? So your question was perfect, because that's exactly what I want to talk about here. So it turns out when you can do DSMs for real products, real systems, like the Wright Flyer and other examples I'll show you, or you can do it for sort of randomly generated systems with different structure. And then you can calculate the graph energy, which is the C3 term, normalized, and you find something really fascinating. When C3, so it's normalized by the number of components or number of nodes. When C3 is less than 1, what you essentially have is a centralized architecture, like a hub and spoke architecture. A hub and spoke architecture is the simplest architecture you can have. It has simple in the sense of it has the lowest graph energy. Okay? So when you look at the DSM, it's essentially, one row and one column is filled in, the rest is all empty. So C3 less than 1. Most real systems, C3 is between 1 and 2. And that's exactly what Simon said, and what we see in many systems is hierarchical architecture. So you have some hubs, but they're sort of regional hubs, right, with components attached to them. And the reason these hierarchical architectures exist, one reason is they have really good properties, but we can understand them. You can assign different branches and modules to different parts of the organization and then reintegrate it. So most real products are C3 is between 1 and 2, as I'll show you. And then we have, and increasingly we're building systems that are like the distributed architecture. There's no hubs, right? It's just a distributed system. And in distributed systems, C3, the C3 term, is greater than 2. And we call those hyper-energetic systems in the graph energy. What does it mean for system engineering? What it means is, if you're operating in a centralized architecture, you have complex components, at least the hub is for sure complex, and the connectivity structure is simple. And then when you're dealing with distributed architectures, you have usually very simple components, but the complexity is in the intricate connectivity of those components. So what does this mean for real systems? I'll give you 2 case studies. One is based on some work that we've done with Xerox. Okay, so Xerox is known for printing systems, and in both of these cases, we look at an older generation product and we look at a newer generation product. And so this is actually on the right side as a machine called the iGen 3, which is a digital printing press, quite successful product. And the picture here shows you the graph of the key components and interfaces. Then you can put that into a DSM and then quantify complexity. And without getting into too much detail here, when we look at the C3 term, the graph energy term, you can see that I'm just going to look at the most likely values. The old system, you can see there's a couple of big hubs there, right? The old architecture had a C3 of 1.36. The new system, the new product, about 1.8. So that's a big step. You're moving from a pretty centralized product architecture to a much more decentralized one. The other thing that's remarkable is that the total complexity of the system has increased by 90%, right, from one to the other. And this allows us to say how much of that complexity increase is in the individual components, how much is in the interfaces, and how much is in the topology of the system. And in this case, you can see it's a big step in all three. Okay, so here's the...
So have you gone back and seen that they really had problems with the new system?
Well, they actually...
Like for example, I think India has the thing with the GM engines thing, where the new system, a new organization was better than the old one, or something.
So, the issues can be many organizational issues, software issues. The key thing we see is that when we show these kind of numbers, 90% increase in complexity, we show this to management. The first reaction is we don't believe it, not possible. But then when you actually look at the overspend, overschedule, the effort in R&D that it really takes to not just design and build them, but qualify them, test them, it is absolutely the case. And we think it's predictable if you did correct complexity assessment.
But this is structural complexity, which is in some ways dependent on functional complexity,
That's right.
which we talked about earlier. So maybe this is required. This 90% increase is warranted.
That's right. So this is an important point. I am not saying that more complexity is always bad. It absolutely is required. Now, you want to keep that complexity increase as small as possible, given what you're asking these machines to do. But absolutely, it's a competitive. If you can handle this well, that gives you an edge over your competitors. So here's the study we did for Pratt on the gear turbofan. So on the left side, you see this is a more classic engine. This is actually the 4096, which is used on the Boeing 777. It's a direct drive two-spool engine. And then here's your gear turbofan. And so we found a 42% increase in complexity. And that's where we got into a lot of debates. Because if you look at the C1 term, that's from 161 to 188. That's maybe 10%. It's actually less than 10% increase. So the gearbox, the variable area nozzle, the mid-turbine frame, there's like 3, 4, 5 key components that were added. That's what people focused on. But that's not the real issue. The real issue, the real driver is in the C2 and a little bit in C3. So the architecture became a little bit more distributed, but not as much as in the Xerox case. But the real increase here is in C2, more interfaces. And a lot of these interfaces are driven by being able to support the gearbox, the cooling, the software, the lubrication, all the supporting systems around it that have been getting more complex. And so 42% increase in complexity compared to a traditional engine. Why would you do this? Well, you do it because you get benefits. You get 15% less fuel economy, and then you get, I think, about 70% less noise. So it's worth doing if you can handle that complexity.
But the issue that you quoted in your second or third chart on the fan plate, that's a C1 issue.
That's a C1 issue on the manufacturing side. That's right. So what the actual source of big increase and delays and so forth, is it going to come out of C1? Is it going to come out of C2, C3? You don't necessarily know that ahead of time. But when you look at the total complexity of the system, that's 42%, not 6% if you just count components. That's really the main message here. So I only have a few minutes left, but I want to just show you something that I think is very cool and potentially fundamental, and that's this idea of a p-point, or that so we keep increasing complexity, making our machines more and more complex to get these benefits. Is it possible that we push this too far? Is there like a transition or tipping point in complexity? And we think there is. And we call that the p-point. And it's pretty interesting. This is well known in graph theory, that when you make a graph denser, you add more links, its properties change up to some point, and then you can keep adding links and not much will change. So the classic measure is diameter. So the diameter in a network is defined as the longest, shortest path between any two nodes. So you take a network, it's a connected network, and you say any pair of nodes in this network, how long is the shortest path between them? That's defined as the diameter. So if you take a random system, and the network density is the number of links that you have in that system, initially the diameter, if it's just a tree structure, meaning there's no loops, it's a long diameter, and then you just add a couple of crosslinks, the diameter drops quickly, and it keeps dropping until sort of this inflection point here, where adding more links doesn't really help you, because the diameter is already so small that you're not getting much benefit. So if this was a transportation system, for example, you could actually calculate, average travel time, things like that. So we can look at this a different way. We can look again at network density, but now graph energy, which is essentially our C3 term. And the red curve shown here is the mean graph energy of so-called Erdős-Renyi graphs, which are randomized networks, but connected. So it's kind of like a background. Think of this as a baseline or background of random systems, but they're connected. And then we can plot the actual products, like our iGen 3, or here's a V8 engine, for example. And what we find is a fascinating thing, which is this point here, this p-point. The way you get the p-point is by taking the graph energy of a fully connected system. So this is a hypothetical system where everything connects to everything else. They don't really exist. Mathematically, you can create that, but physically, we don't see that. But you take this and you intersect a horizontal line with the red curve. And that intersection is known as the p-point. And the way you interpret this is the low density equivalent of a fully connected system. And so what we find again and again when we plot actual products against this is that actual products are at the p-point or below the p-point, but rarely do we find a product above the p-point. And so the hypothesis is that if you go past the p-point, you've added density, you've added complexity, but you're not getting much benefit out of it. That's essentially the message. And that's why we think it's a critical point. And there's other information that tells us that this p-point is a very special thing. So I've shown you this intersection here. That's the upper left graph. And you can also increase the size of the system and then say, what's the critical density? The critical density is where you essentially reach the p-point. Oh, by the way, mathematically, that's also the point where the DSM, that matrix, becomes full rank. And then in full rank is a big deal in linear algebra, so something magical happens at the p-point. The other remarkable thing is you can calculate, even though the critical density itself is size dependent, what's independent of size is the critical nodal degree. In other words, how many connections per part, right? How many links per node? And that's the red line, which is about at 6. So a nodal degree of 6, regardless of the size of the system, is where the system reaches the p-point and becomes critical. And so, do you remember with the Wright Flyer, I said it had 5 connections per part? Just below that, there's work in network resilience, how many links per node. such that the system doesn't fall apart for either a random attack. This is a random attack versus a targeted attack. And again, these contours here are the contours of equal number of connections per node. And then Dan Whitney, who's retired now, but great colleague at MIT, also reverse engineered a lot of assemblies, mechanical assemblies, and then looked at number of X's, number of interfaces in the matrix versus number of rows. And you can see this correlation here, y equals 6.3 minus that the constant term doesn't matter. But what matters is that it's a 6. So this is a really, really important thing, is that in systems, if you go beyond 6 connections per part, you're essentially pushing past the P point. And we think that's the reason why many real products and systems are below that.
It's also true with the humans. Miller's, George Miller's.
Right.
Definitely. Definitely. So there's a lot of things about that. So let me. I think I'm running late here. So I just want to talk about the structural complexity. And you mentioned Miller's work on the magic number 7 plus or minus 2. So our perception of structural complexity, you can measure it absolutely, but then how does that drive system development cost? It drives it through what we call complicatedness. So when you say a system is complicated, that's the perception of the real complexity. It's a human interpretation of complexity. And that's where this curve that we looked at in the molecular studies comes in. So the actual complexity is on the x-axis, and then the actual effort to deal with this goes up nonlinearly. That's the red curve. And it's driven by, the complexity itself, the modularity or design encapsulation that you have. More modularity makes the system easier to understand, easier to deal with. The amount of novelty is the first time you're dealing with a system, or have you dealt with it before? And then, the cognitive capability, cognitive bandwidth, and even cultural effects. The implication here is that a 42% increase in complexity would lead to a 69% increase in R&D costs. And so now this allows us to complete the picture. We have functional complexity and structural complexity, and now we need to add the organizational complexity. How are you mapping your different teams, your team structure, to the different parts of the architecture? And because when you're trying to, budget a new product development process, what you really care about is the non-recurring engineering cost and the schedule. So structural complexity drives organizational complexity, which can backdrive even to functional complexity.
So Conway's law, no, that. What is it?
Conway's law is basically it says that the product architecture will mirror the organizational architecture.
What we call congruence.
Yes, exactly. So the message here to finish is that we think that we need to start doing complexity budgeting in our projects. We budget for everything else: mass, power, volume, financial budgets, but we typically don't budget for, this is your complexity budget, and you have to live within this. And so the question is, what level of complexity will maximize value? So it turns out, this is fascinating, it turns out you just need 2 curves to figure this out. One curve is performance versus complexity. So this looks like an S curve, right? And you can, that's the equation for it. Basically, we know this, that for a given architecture, you can get more and more performance early on, right? So airplanes improved a lot in the early 20th century. And now every % improvement, we have to really buy it with a lot of increasing complexity. We're kind of, in aircraft engines, we're definitely in the flat part of that curve now. The other curve is the one that we looked at. It's effort versus complexity, and that's the nonlinear curve. And so it turns out that there's 2 exponents. One is this n, which is the shape of this S curve. And then the other one is the m, which is the exponent on the effort versus complexity. You've all heard the heuristic called KISS, right, in system engineering. Keep it simple, stupid, right? As simple as possible. It turns out it's a good heuristic, but only if n is smaller than m. So the value maximizing design is the one that is the lowest complexity given the performance that you need. However, if n is greater than m, it turns out there's an optimal point in the value curve. And so you would go for a higher complexity solution because it gives you more value. Okay? So basically, if you believe in complexity-based budgeting, you can now think about isocomplexity, which is, okay, this is your complexity budget, and now you can decide how to invest it. Do you want more components, but simpler ones, right, in a more complex arrangement, or do you want fewer components, but on average, each component is more complex? So you need to be on this surface. That's what complexity budgeting means. So let me finish with this first law. This is not widely accepted, so I'm just going to throw it out there. The first law of thermodynamics says the law of conservation of energy states that the total energy of an isolated system is constant, and you can transform energy from one form to another, but you cannot create or destroy it. Right? That's total energy is kinetic plus potential plus internal energy. And it's fascinating. This first law of thermodynamics, we take it for granted today. It took almost a century of battles for people to agree to this law. So I think the first law of system engineering is also a conservation law. And it's basically the law that given a set of fixed functional requirements and associated performance levels, that the total complexity of the system is conserved. And you can trade complexity between components, interfaces, and topology, but you cannot decrease it beyond some minimum level. And so then total complexity is the C1 plus C2 times C3 plus this W term, which we don't quite know yet what it is. It's kind of the equivalent of internal energy, but that's essentially due to the uncertainty as to what the base level for alphas and betas should be. So that requires more research. Let me skip this, and then I'll just summarize. So structural complexity has been increasing in many of our systems, and it's due to, since the Industrial Revolution, it's happening because competition, it's driven by functional complexity, drives structural complexity, drives organizational complexity. The human cognitive bandwidth limitations lead to the fact that as we increase complexity, we get worse and worse at it. It takes more effort. It's superlinear with an exponent of about 1.5. There's a rigorous measure of complexity based on graph energy. It satisfies Weiker's criteria. It's the C1 plus C2 times C3, and C3 is the graph energy. And where we need to go in this field is complexity-based management. And the good news is there's some really important anchors out there that we can use. The P point as a critical transition point, the critical nodal degree of 6, and then the idea of isocomplexity-based budgeting with clear targets. So I would state to you that conservation of complexity is the first law of system engineering, and I'm happy to debate that.
Thank you, Ali. So we can have questions.
Did we do too long, or?
Yeah, there
Sorry.
there is a little time, but I think there's time. Yeah, but there is no one shown yet, so.
Yeah.
Yes.
How do you get the curve between complexity and performance? The S curve?
How do you get the S curve? So I think either you get it empirically by looking at products in a certain area and what performance levels they have. The best example I've seen is photovoltaic cells. Photovoltaic cells, NREL, the National Renewable Energy Lab, what's the world record for efficiency on photo? So you can see it's absolutely an S curve. It's a very sort of shallow S curve, and then somebody comes up with a new idea for, like gallium arsenide, much better efficiency. And starts a new S curve. And then you have real points based on real products. So you can fit the S curve to the real points, calculate your K and N coefficients, and then you have it. But it's kind of like after the fact, right? The other way to get it is if you really understand the physics pretty well, you have governing equations, and then you can make some assumptions as to how good do you have to be to reach this level of performance, and when do you hit fundamental limits. And that would be sort of deriving the S-curve based on, fundamental governing equations. But that's how you would do it. Two different ways of doing it.
That looks like the rise time of a system.
Yeah. And this could be, in some technologies, this is like 20 years. And then for other technologies, it's like 100 years. Yeah.
You could probably add some sigmoid function too, right?
So DSM is really cool. A lot of companies have been implementing this for doing some structural analysis for project development, project management. I'm actually pretty curious to see if you see or have been able to analyze products that were developed using formal methods and formal analysis of their design engineering process, like implementing DSM, and the products they actually get out of the other end.
That's a great idea. We haven't done this. So mostly people use, this is, the product-based DSM. Yeah. You're describing sort of task-based DSMs or process-based DSMs, but to actually see their causal link, like if you're using formal methods, do you get better products out of it? I don't think we know. I don't think we know. It would be interesting, but I think that you'd have to get the data. Mm-hmm. Great idea, yeah.
The conservation of complexity. In engineering, we know about function sharing. And the higher the degree of function sharing, the lower the complexity. Doesn't that...
So are you talking in software or in mechanical systems?
Anything really, but I'm thinking of this paper by Ulrich and Searing with the Neo Clipper, which is the best possible thing that you can imagine.
But I think it's wrong. It's wrong because when you do function sharing, in other words, one component does multiple functions, it's true that the part count will go down, but that doesn't mean the total complexity goes down, because typically then each part gets more complex, right? And the requirements for each part might go up. So the number of components goes down. Maybe the number of interfaces goes down too, but the alphas will go up. The alphas are the component complexities. I mean, you push this to the ultimate limit where one single component can do many, many different functions. And we have examples like this. But that single component will be quite complex. And so function sharing is just redistributing the complexity in the system. I don't think it's actually lowering the total complexity.
So nowadays people think about automating everything, right? So why do we care about 6 anymore? Because hopefully these automated systems will know it.
Okay, so...
But I'm just throwing some really weird question. I don't know whether it's...
No, it's not weird. I don't think it's weird at all. I think basically what you're doing when you're automating a system is in a non-automated or only partially automated system, you have a human in the loop, right? So the human, like in the Wright Flyer, is the controller, essentially, right? Pushes buttons, takes actions. So you're replacing the human vision, cognitive functions, sensory motor functions with software, right? And electromechanical actuation. Basically, that's what you're doing.
I'm thinking of more out things where the machines are designing also.
Okay, I'm not quite there yet.
Okay.
But so the classic so you take the human out of the loop. So the human is no longer necessary, or there's different levels of
maybe you just specify requirements.
But then the software that you need, especially if the system, this is with self-driving cars. So the amount of sensors you need, the software you need, the different use cases goes way up, right? And so, in some sense, you've taken the human out, but you've actually potentially increased the complexity a lot. Now, machines that can design other machines, I haven't thought about it. So, yeah.